everyone, Simi here. I'm excited to announce an upcoming multi-agent-based development course for senior Gen AI folks, led by the brilliant Abhinash Mishra.
All right, let's get into it. You ever look at a product you love and just wonder, how did this even happen? How did it go from just an idea to this thing I use all the time? Well, it's not magic, that's for sure. It's a roadmap. And we're not talking about some boring old school map. This is a living, breathing guide for an incredible journey. So what's the big secret, right? Is it just jamming in more features than the competition? Having some super slick design? Nah, not really. The secret is the process. It's the roadmap. Think about it like a road trip. You wouldn't just jump in the car and start driving aimlessly, would you? Of course not. You'd have a destination. And that's exactly what we're going to map out. And just like any great road trip, the very first thing you do, before you even think about snacks for the car, is figure out exactly where you're headed. In product development, that destination, well, it's defined by your metrics. This is your map. This tells you if you're going in the right direction. Now hold on, we're not talking about those vague business goals like, let's increase engagement. What does that even mean? No, we need to get specific with customer-centric metrics. These are all about measuring success from the only point of view that actually matters, your customers. Did we solve their problem? Do we make their life just a little bit easier? That's what we need to measure. Okay, let's make this super concrete. Imagine we're building a banking app. A good metric isn't just how many people logged in today. A great metric is, can a user transfer funds in under 30 seconds? Why? Because that number is directly tied to a real customer value, saving them time. See that connection? That's how you turn a fuzzy goal into something that genuinely makes a customer happy. So we've got our destination locked into our GPS. Awesome, but now we need an engine to actually move the car forward. In the world of modern products, that engine is this incredibly powerful process called the build, measure, learn cycle. It's what drives the whole journey. And you know what? It's a beautifully simple loop. First, you build a tiny, testable piece of your idea. Then you put it out there and you measure how real people actually use it. You get that real-world data. And finally, the most important part, you learn from that data. You figure out, okay, what's next? Do we keep going? Do we change direction? Or do we scrap this idea and try something else? And then the cycle starts all over again. It's continuous. And you really see how brilliant this is when you put it next to the old way of doing things, the waterfall model. That's where you'd spend like a year building a massive product based on a bunch of assumptions, and then have one huge nail-biting launch day. This new way, the iterative cycle, it's more like a smart GPS. It's fast, it's flexible, and if you take a wrong turn, it helps you reroute based on real feedback. It massively cuts down the risk of building something nobody actually wants. All right, so we've got our destination and we've got our engine. But what do we actually build on each little leg of the journey? How do we come up with the blueprints for each one of those build cycles? Well, that's where your iteration strategy comes into play. Often, the whole thing kicks off with what's called a minimum viable product, or an MVP. But let's be really clear on this. An MVP is not a sloppy, half-finished product. It's the absolute smallest, simplest thing you can build to get that build, measure, learn engine started. The goal here isn't to build a perfect product. It's to get the maximum amount of learning with the least amount of work. And the way we figure out what to put in that MVP and every single iteration after it is with this fundamental little building block, the user story. And this is such a powerful tool because it forces a huge mental shift. You stop thinking about building features and you start thinking about solving problems for actual people. The structure itself is genius in its simplicity. As A, that's who it's for. I want to, that's what they need to do. But honestly, the secret sauce, the part that really matters, is that last bit, so that. That's the why. It forces you to connect every single piece of work to a real benefit for the customer. If you can't fill that last part in, maybe you shouldn't be building it. Here's a perfect example from our banking app. We're not just building a transaction history page. No, we are enabling a customer to track their spending. You feel the difference there? One is just a feature. The other is a solution to a very real human need. And that is the power of a well-written user story. But hey, how do you know when you're actually finished with a story? That's where acceptance criteria come in. Think of these as a simple checklist that defines what done looks like. For our story, it might be the list must show the date, the store, and the amount. It gets rid of any confusion and makes sure everyone on the team is on the exact same page. Okay, we are so close. We have our destination, we have our engine, and we have our blueprints, the user stories. The last piece of the puzzle is how we organize all those blueprints into a practical turn-by-turn navigation system that our team can actually follow. And that is your product backlog. You can just think of the product backlog as the master to-do list for the entire product. It is the single source of truth for every user story, every bug fix, every little task the team might ever need to work on. It's all there in one place. And here's how you bring order to that chaos. First, you start big, with broad themes called epics, like improve account security. Then, you break those big epics down into those small, specific user stories we talked about. You estimate how much effort each one will take, and then, and this is the most important step, you prioritize them based on what? On customer value, the exact same value we defined way back at the beginning. The stuff that delivers the most value goes right to the top, and that's what the team builds next. So here's the one thing to take away from all of this. From those high-level, customer-centric metrics that define your entire destination, all the way down to the tiny, individual stories in your backlog, every single part of this modern roadmap is designed to serve one, and only one, ultimate purpose: to consistently deliver real, meaningful value to your user. That's it. Look, this isn't just some abstract theory. It's a real, practical toolkit you can start using today. So I'm going to leave you with a question to chew on. What's a small idea you've got rattling around in your head? And how could you use this build, measure, learn cycle to test it, even in a tiny way, maybe even this week? Thanks for tuning in.
Folks, I hope you are liking our content and it is adding up nicely in your skill set database. If so, hit the like and subscribe button.
All right, today we're building something not with hammers and nails, but with pure logic and code. We're going to dive into the essential blueprints that every developer needs to turn a great idea into a solid reality, the software design document. I mean, that's the million-dollar question, right? You've got this brilliant idea for an app, but without a plan, that brilliance can just dissolve into this tangled-up mess of code that's not just hard to build, it's impossible to maintain. Look, you wouldn't build a house without a detailed architectural plan, and you really can't build solid software without one either. These design documents, they're the bridge, the critical bridge that takes you from a fleeting idea to a concrete functional system that actually works. So, where do we even begin? Well, we start with the single most important person in this whole process, the user. Yeah, before we even think about writing a line of code, we have to understand what people are actually going to do with our software. This right here, this is the bedrock, the foundational question. We're not just building a random list of features. No, we're solving a real-world problem. And to do that, you've got to step into the user's shoes and really map out what their goals are. Our first tool for the job is the use case diagram. And honestly, it's basically a simple map. On one side, you have your actor, that's our user. On the other side, you've got the system. The diagram just shows all the ways the user needs to poke and prod the system to get something done. So let's imagine we're building an account management system. The user's goals are pretty clear, right? They need to see their balance, they need to deposit or withdraw funds, move money around, and check their history. Every single one of these is a use case, a specific, absolutely critical interaction our system has to support. No exceptions. Okay, so now we know what the user wants to do. The next logical question is, how? How is our system actually going to respond to make all that stuff happen, step by step? You know, a modern app isn't just one big block of code. It's more like a team of specialists. You've got the user interface, back-end services, databases, and they all need to communicate perfectly. So how do we choreograph that really complex dance? Well, that's where the sequence diagram comes in. Think of it like a script for all our software components. It maps out the exact order of messages that get passed between different parts of the system to get a job done. It shows us precisely what happens and, crucially, in what order. Okay, let's bring one of those use cases to life. A customer wants to view account balance, so they tap a button on the screen. Instantly, behind the scenes, the UI sends a request to something called the account service. That service then goes and asks the database for the info. The data then flows right back along that same path. That is the hidden dance happening behind every single click. All right, we've mapped out the actions and the system's dynamic dance. Now it's time to get down to the foundation, the core, static structure of our code and our data. First up, the class diagram. Now, if you're working with a language like Java, C++, or Python, this is your absolute core blueprint for the code. It defines the nouns of your system, things like an account class or a customer class, along with their properties and what they can actually do. And for the data itself, we use an entity relationship diagram, or just an ER diagram. This is the blueprint for the database. It doesn't care about code at all. It's focused purely on data entities, their attributes, and most importantly, how they relate to each other, like making sure one customer can have multiple accounts. Just think of them as two sides of the same coin, really. The class diagram designs the application's brain, the code. The ER diagram designs the system's memory, the database. They do totally different jobs, but they have to line up perfectly for the whole thing to work. Now, when you're designing that database, there's this critical process called normalization. The goal is super simple. Don't store the same piece of information in multiple places. If you do, you're asking for a data corruption nightmare. By properly organizing our tables, we create a database that's efficient, reliable, and just trustworthy. Okay, our internal structure is sorted, but how's our system going to talk to the outside world? How will a mobile app or maybe another company's service interact with it? For that, we need a clear public contract. And this is how we build that public contract, the API. We start with a use case, like view account balance, and we translate it into a technical address, an endpoint. We define exactly what data goes in and what comes out, and then we formalize the whole thing in an OpenAPI specification, often using a tool like Swagger. And here's where it gets really, really cool. Once you have that OpenAPI spec, tools like Swagger can automatically generate interactive documentation where anyone, any developer, can test your API live. It can even generate the client-side code for you in dozens of languages. It is a huge, huge accelerator for development. So let's take a breath. We've designed the user interactions, the internal logic, the code, the database, and the public API. Now, it's time to zoom all the way out and look at the master blueprint. You see, each diagram we've talked about is like a different lens, focusing on a specific layer of detail. But they're not just isolated documents. The real magic is how they all connect together into one single coherent design where every single piece has its purpose. So how do we actually represent the entire system? The whole forest instead of just the individual trees. We need that final bird's eye view. And this is it, the high-level architecture diagram. This is the true master plan. It intentionally ignores all the little details and instead shows the major building blocks, the services, the databases, the gateways, and how they all fit together to create the final product. And here's how it all comes together for our account management system. The user interacts with the client app. That app talks through the API gateway, which, remember, is defined by our OpenAPI spec. The gateway routes requests to a specific microservice whose code is structured by our class diagram. That service then reads from and writes to the database, which is perfectly organized by our ER diagram. See? Every single blueprint has its place in the final picture. So there you have it. From a simple user need all the way to a complete architectural plan. That's the power of a good design process. It turns chaos into clarity, and it turns ideas into reality. So the only question left is, what are you going to build?
Folks, I hope you are liking our content and it is adding up nicely in your skill set database. If so, hit the like and subscribe button.
Hey everyone, and welcome. So if you're a Java or a Python developer building, well, anything modern, you know that proving your app works reliably isn't just a nice-to-have, it's everything. Today, we're going to dive deep into a tool that totally changes the game for integration testing, test containers. Let's get right into it.
I mean, this is the big question, right? It's one thing for your code to work on its own, but how do you prove that all the different pieces, your service, that database, the message queue, can all talk to each other perfectly? Not just once, but every single time. And as we all know, that is way easier said than done.
To really get a feel for why this is so critical, let's imagine a scenario where failure is just not an option, a personal banking system. Yeah, when you're dealing with people's actual money, good enough testing just doesn't cut it. The stakes are incredibly high. So let's break down what looks like a simple action. A user clicks a button to book a fixed deposit. But behind the scenes, it's like a complex chain reaction. The request hits your API, your service has to write it to the database, a confirmation message gets fired off to a queue, and then some other service has to pick it up. If any single one of these links in the chain breaks, the whole thing falls apart. So how on earth do you test this entire flow reliably? Well, this brings us right to the heart of the problem with how many of us have been doing this for years. The issue often isn't the test we write, it's the environment where that test runs. That classic shared dev environment. You know the one. It's usually the source of our biggest nightmares.
And here it is. This is the root of so much pain. One single database, shared by every developer on the team, every new feature branch, every single automated build. You can see how this is just a recipe for absolute chaos, right? It leads to tests that are anything but consistent or reliable.
And this slide just lays it all out, the world we live in versus the world we want. On the left, you've got the traditional setup. It's shared, it's inconsistent, someone has to manage it by hand, and somebody else's work can break your tests without you even knowing it. But what we're all dreaming of is on the right, an environment that is totally isolated, perfectly repeatable, and completely automated. The consequences of that old way are, well, they're painfully familiar, aren't they? You've got those flaky tests that pass on Tuesday but fail on Wednesday for no reason. You get the classic, well, it works on my machine argument. You're stuck waiting around because the dev database is down again. And of course, you're constantly running into test data conflicts with your teammates. It's just a huge drain on everybody's time and energy. So, how do we escape that mess and get to the promised land? Well, this is where our hero, test containers, enters the story. The solution is to use real dependencies, but to spin them up on demand, only when you need them. So what exactly is test containers? It's a fantastic open source library that lets your test code all by itself spin up a fresh, real version of a database, a message broker, really anything you can put in a Docker container. And the most important word here is throwaway. You use it for one single test run and then poof, it's gone.
This quote really nails the whole benefit. Let's look at the keywords here. You are running tests against real services. This isn't a mock. It's not some in-memory substitute. You are testing against a real Postgres database or a real RabbitMQ queue, but, and this is the magic, it's in a perfectly clean, totally isolated environment that belongs only to your test and no one else.
And the whole process is just beautifully simple. Your test kicks off, it makes a quick call to the test containers library. On the fly, it spins up the exact Docker container you asked for. Your test code connects to this brand new instance and does its thing, and then, as soon as the test is done, whether it passed or failed, that container is automatically destroyed. No mess, no manual cleanup. It's fantastic.
Okay, that's enough theory. Let's see what this actually looks like in practice. We're going to use a little project from the source material, a fast-track savings goal system, to make this whole concept way more concrete.
So the mission is simple. We're going to test a feature that creates a new savings goal for a user. And the test has to prove that this action correctly writes the data to a real database. No shortcuts, no mocks, we're testing the actual integration.
And just look at how clean the code is. For all you Java folks using JUnit, you just slap on a couple of annotations, @test containers and @container, and the framework just handles everything else. And for Python developers using PyTest, it's just as slick. You use a simple with statement, and it manages the whole lifecycle for you. In both languages, it's simple, it's declarative, and it's super easy to read.
Now, you're probably thinking, wait, how does my app know the address of this temporary database? And that right there is the secret sauce, dynamic properties. Test containers figures out the random port and address of the new container and just feeds it to your application at runtime. That means zero hard-coded connection strings in your test files. It just works.
All right, let's start to wrap this up. Let's go over the key takeaways and really hammer home why this approach is so powerful for building software you can actually trust. So, what do we actually gain from all this? First, we get true test isolation. No more conflicts, no more who broke the dev database. Second, we get high-fidelity testing. We're using the real deal, not some flimsy imitation. That, in turn, leads to a huge boost in developer productivity, because we're spending less time fighting with broken environments. And the ultimate payoff? Perfect repeatability. If a test works on your machine, it's going to work on the build server. It's going to work everywhere, every time.
And that brings me to the final thought I want to leave you with. I want you to take a hard look at your own tests. Are they truly reliable? Do they give you real confidence every time you push a change? Or are they just lucky, passing only when the stars align and the shared environment happens to be in a good mood? With test containers, you don't need luck. you can choose reliability every single time.
Folks, I hope you are liking our content and it is adding up nicely in your skill set database. If so, hit the like and subscribe button.
All right, let's talk about something that separates the pros from the amateurs. Writing code that actually lasts. I'm not talking about code that just works for a week. I mean code that you and your entire team can come back to in 6 months and not be completely terrified of. We're going to break down the key principles for building software that's clean, maintainable, and ready to scale. Come on, you know the feeling, right? You wrote some feature, it passed the tests, and you shipped it. But now, months later, you get a ticket for a tiny change, and your stomach just drops. You know that touching that one little piece of code could bring the whole thing tumbling down like a house of cards. We've all been there. But here's the great news. It absolutely doesn't have to be that way. The gap between that fragile, terrifying code and something that's robust and flexible, well, it really just comes down to a few core battle-tested principles. And today, we're going to dive right into them. So let's start with 2 of the most foundational and honestly most impactful principles you can start using like right now. Let's get into kiss and dry. Okay, just look at this. On one side, you have this over-engineered mess. It's got nested conditions, weird temporary variables. You have to be a detective just to figure out what it's trying to do. But on the other side, it's simple. It's clear. You can read it like a sentence and know exactly what its job is. And that leads us to our very first principle. And that principle is KISS. Keep it simple. It's this powerful, constant reminder that complexity is your enemy. Simple code is just easier to read, it's easier to debug, and it's a heck of a lot easier to maintain. You should always be asking yourself, is there a simpler way to get this done? 9 times out of 10, there is. And now for another classic problem, repeated logic. You see it everywhere. Someone writes a bit of code, it works, so they copy and paste it somewhere else, and then somewhere else again. You've just created multiple sources of truth. If that business rule changes, you have to go on a scavenger hunt to fix it everywhere. The solution? Pull that logic out into one single reusable place. Now you only have one place to change. So much better. This brings us right to our second simple rule, DRY, or don't repeat yourself. The idea is that every single piece of knowledge or logic in your system should have one and only one place where it lives. This isn't just about avoiding typing. It's about creating a single source of truth that makes your entire system more reliable and predictable. Okay, so with KISS and dry as our foundation, we're ready to level up. Let's move on to a powerful blueprint for designing software, the solid principles. If you're building anything bigger than a simple script, these are the pillars that will keep it from falling over. We're going to start with the S in solid, the single responsibility principle. And honestly, this quote says it all. A class should have one job, one focus. If you find yourself changing a class for multiple unrelated reasons, that's a huge red flag that it's doing way too much. And here's a perfect example of what that looks like. On the left, we have one monster class trying to do everything. It's handling business rules, it's talking to the database, and it's sending emails. It has 3 different reasons to change. The right way to do it? Give each job its own dedicated class. Now each one is small, focused, and so much easier to understand and test. Next up is O in solid, the open-closed principle. Now, this one sounds a bit like a paradox, but it is pure genius. It means you should be able to add new features to your system without ever having to go back and change the old existing code that you already know works. This slide shows you the 2 paths. The risky path is constantly opening up old code to add new if statements every time there's a new requirement. That's fragile. The compliant, robust path is to design your system so new features are just new pieces of code. You extend the system's behavior without ever touching that stable core. That's the magic of the open-closed principle. Another massive part of solid is the D, the dependency inversion principle. This is all about decoupling your code. Your high-level business logic shouldn't know or care if it's saving data to a SQL database or a cloud service or a text file. It should only depend on an abstract concept, like a repository. This is what allows you to build systems that are truly modular, like snapping Lego bricks together. So we've talked about how to design individual classes, but now let's zoom out. How does this apply to the whole system? How do we get all these different parts of our application to communicate with each other cleanly and effectively? A huge concept here is separating what your system knows internally from what it shows to the outside world. Think of an entity as your internal truth. It's the model that perfectly matches your database tables. A DTO, or data transfer object, on the other hand, is your public contract. It's what you show the world through your API. It's carefully designed to only expose what's necessary, hiding all your internal details. This is critical for both security and long-term maintainability. So, how does this actually work? Let's trace a request. First, a request hits your API, and it's carrying a DTO. The controller grabs that DTO and passes it off to a service layer where all the real business logic lives. The service then carefully maps the data it needs from the DTO over to an entity, and finally, a repository takes that fully formed entity and saves it to the database. See that clean flow? Each layer has exactly one job. But wait, how does that service layer get the repository it needs? Well, that brings us to a beautiful concept called dependency injection, or DI. And the analogy's perfect. Think about building a car. Your car needs an engine, right? But the car factory doesn't build the engine from scratch inside the car. It just asks for an engine to be provided, and then it gets installed. That's the whole idea of DI. Look at the difference here. Without DI, you get tight coupling. The class is responsible for creating its own dependencies. Everything is bolted together, it's rigid, and it's a nightmare to test. But with DI, you get loose coupling. The dependencies are just handed to the class from the outside. This makes it incredibly flexible, modular, and super easy to test because you can just hand it a fake dependency. So why do we bother with all this? Well, the payoff is huge. You get way more flexibility to swap out components. Your code becomes infinitely easier to test. And most importantly, by reducing all that tight coupling, your code becomes simpler to maintain and understand. It is a genuine cornerstone of modern software design. Whew, we have covered a lot of ground, from simple rules all the way to architectural blueprints. So let's boil it all down to a few key takeaways you can start thinking about today. Yeah, you're seeing this quote again, and for a very good reason. If you remember only one single thing from our time together, let it be this. The next time you're about to add a method to a class, just stop and ask yourself, is this really part of its single core job? Just answering that one question honestly will radically improve your code. And I love this because it perfectly captures the spirit of KISS and just elegant design in general. Great software isn't about cramming in more features and more lines of code. It's about refinement. It's about finding the absolute simplest, clearest way to solve a problem. It's about removing everything that isn't essential. And that brings us to the real question. It's great to talk about this stuff, but the real work starts now. So think about your own code. Maybe it's finding and removing a piece of repeated logic. Maybe it's simplifying a crazy complex function. Or maybe it's finally splitting up that one class that's doing way too much. What is the one principle you can apply today to make your code just a little bit better?
Folks, I hope you are liking our content and it is adding up nicely in your skill set database. If so, hit the like and subscribe button.
You know, when you check your bank balance on your phone, you're not actually looking at a pile of money somewhere. You're looking at a number stored in a database. And that number, along with the entire system that protects it, is all built on computer code. The safety of your money, literally, depends entirely on how well that code was written. So, just how secure is it? Let's find out. It sounds kind of crazy, right? Something out of a heist movie. The idea that a simple, everyday feature like a search bar could be the key that unlocks an entire bank. But what if I told you it's not just possible? It's one of the most common vulnerabilities that attackers look for? Think about it. Every single thing you do in your banking app, logging in, checking a transaction, sending cash to a friend, is an instruction. That instruction is handled by code. And that code acts as the walls, the doors, and the guards of your digital vault. If there's even a tiny crack in that code, the whole thing is at risk. Okay, so let's zero in on a feature we've all used a million times, the transaction search bar. Seems completely harmless, doesn't it? You type in a word, it shows you what you spent. But to a hacker, this little box is a potential open door, leading straight into the bank's most sensitive data. So, a typical user, you or me, might type groceries into that search bar. Behind the scenes, the app's code politely asks the database, hey, could you please get all the transactions labeled groceries for this particular user? It's a clean, simple request. Everything works just like it's supposed to. So, how does an attacker twist that simple request into a weapon? They use a technique called SQL injection. Now, don't get hung up on the name. Just think of it like this. The attacker isn't just giving the search bar something to look for. They're secretly whispering a whole new set of instructions into it. And just look at how subtle the attack is. On the left, you've got a normal, honest search for groceries, but on the right, that weird-looking bit of text is the attacker's input. It looks like nonsense, but to the database, it's a very specific command that basically says, forget whatever you were looking for. Instead, just show me everything, because 1 always equals 1. They've completely hijacked the conversation. And right here, you can see the catastrophic difference. Instead of just seeing your own grocery bills, the insecure app now just spills everything. It dumps every single transaction from every single user in the entire bank. Your data, my data, everybody's data, all laid bare because of one cleverly crafted line of text in a search box. So the big question is, how do we stop this? Well, thankfully, this isn't some unsolvable problem. In fact, secure developers have really effective ways to slam the store shut. It all comes down to building the code correctly from the very beginning by following 2 fundamental principles. These 2 defenses work together beautifully. First, you have the sealed envelope. This means instead of mixing the user's search term right into the database command, the code keeps them separate. It puts groceries in a sealed envelope and tells the database, hey, this is just data to look for, it's not an instruction to follow. The second defense is like a bouncer at a club. It checks everything that tries to come in and immediately throws out anything that looks suspicious or doesn't follow the rules, like that bizarre string of attack code we saw earlier. And this really gets to the heart of secure coding. It's a whole mindset. Programmers have to work under the assumption that any information coming from a user could be malicious. The system has to be designed from the ground up to strictly separate the what, the data, like groceries, from the how, the instructions for the database. Now, SQL injection is a huge threat, for sure, but it's just one of many. Securing a bank is like defending a castle that has tons of gates, windows, and secret passages. You can't just lock the front door and call it a day. You have to secure every single possible way in. And the threats come from all angles. For example, an attacker might use something called cross-site scripting. This trick gets your own browser to run malicious code, which could let them steal your login information right from your own computer. Or they could hunt for something called broken authentication. They're looking for flaws that let them just skip the login screen entirely and impersonate you without ever needing your password in the first place. And sometimes the weakness isn't even a complex flaw in the code. It can be a simple security misconfiguration, like a developer forgetting to change a server's default password. The main point here isn't to memorize all these attack names, but to understand that the defense has to be layered, protecting every possible entry point. So after all this technical talk, why does any of it matter to you, the person just trying to pay a bill on their phone? Well, it matters because the safety of your entire financial life rests on developers having this security-first mindset every single day they write code. So what are the really big takeaways from all this? First, great security never happens by accident. It has to be deliberately designed from the very start. Second, every single box you can type in, from a search bar to a login form, is a potential point of attack. Third, the strongest systems use multiple layers of defense, like our sealed envelope and our bouncer working together. And maybe most importantly, the quality of that invisible code is the only thing standing between your money and someone who wants to take it. So the next time you look at a simple login form on a website, I want you to remember the invisible battle that's happening right behind it. It's a constant, deliberate effort by good developers to treat your password as precious data and not as a hidden command. The security of your entire digital life really depends on them getting that one simple, critical distinction right every single time.
Folks, I hope you are liking our content and it is adding up nicely in your skill set database. If so, hit the like and subscribe button.